Hey there, hi there, ho there. Welcome back. Unit 6, volcanoes. Ooh, it's gonna be hot. Because they're hot. Alright, so, now I think we're gonna start to, last unit we talked about the minerals and rocks, and now we're gonna get back into some of those natural hazards and disasters. And volcanoes are a great place to start. You can still tie that back into plate tectonics and what's going on there to create volcanoes. So let's jump into this, shall we? You know what? Before we do, let me give you the first part of the super secret code. It is the number 1. You got me? The number 1. One more time. The number 1. All right. So let's just go over some basics of volcano. So what is a volcano? Well, technically speaking, it's an opening in the Earth's crust through which lava, ash, gases, and Earth's internal heat escape. So it's like an escape route for all that heat that's kind of bottled up inside the Earth. When any of this material escapes, it causes what's known as a volcanic eruption. Eruptions can be explosive, sending material high into the sky, ash, and all kinds of fun stuff. But, volcanoes can actually be quite calm with very gentle flowing material. Not all volcanoes are the same. Some are violent, some really aren't. When we think of a volcano or any natural hazard, we think, oh man, we think of it at its worst. Well, a lot of times in volcanoes, everything's just fine. Sometimes, though, it's not. But anyway, not all volcanoes are the same. There are different processes in formation, so how they form. And again, it depends on tectonic settings. So kind of going back to plate tectonics. Do you remember what process drives plate tectonics? We'll review. Remember what's responsible for shifting and moving all the plates around? Do you remember? Mantle convection, of course. You see, you're right. You're right. I'm like Blue's Clues. Yeah, good answer. So mantle convection is always directly or indirectly involved as the cause of volcanism, as it is the driving force of plate tectonics. So you're moving hot mantle material around. When you're moving that hot mantle material around, it can melt material, causing it to turn to molten rock, liquid rock. And that molten material could make its way through the crust to the surface of the Earth, erupting as a volcano. So that can happen in a number of different spots. Again, in the middle of continents, at divergent boundaries, at convergent boundaries, ocean to continent, continental crust to continental crust, again, divergent boundaries, hot spots. It can happen in a lot of different spots. But the essential thing is some upwelling of mantle convection, causing material to melt. That melt material is less dense than the surrounding material, so it will begin to rise. And as that material rises, it could erupt to the surface of the Earth, whether it's dry surface or underneath the ocean. The surface of the Earth, there's still surface underneath the water, so you can still get underwater volcanoes. But in any case, when that material reaches the surface, you could have an eruption. All right, so that's mantle convection is what drives it. Now, there's two terms when we're talking about volcanoes that we really want to make sure we have secure. First is magma. Magma is molten rock below the Earth's surface. So you get this molten material below the Earth's surface. It's moving up, it's below the Earth's surface, it's called magma, magma, magma. But then when it finally erupts onto the surface, that's when we call it lava. So like two different names for the same thing. Magma when it's down here, lava when it's up here. So again, inside the Earth, magma, 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 and as soon as it erupts, lava, lava, lava. That's the name. Two different names for the same stuff, this molten rock material. So, where does the magma come from? So this is liquid, hot rock. Where does the magma come from? Remember, we have the solid crust, a mostly solid mantle, the liquid outer core, and then the solid inner core. So where does liquid magma come from? Well, in this case, nope, you're wrong. It's not the liquid outer core. In fact, nowhere close. Because of mantle convection, which is just moving heat, the hot spots, there are certain hot spots in the mantle, which is mostly solid. As it interacts with the crust, there's some material at that kind of boundary, kind of the upper mantle or up into the crust, that begins to melt. So some solid rock actually beginning to melt. These little pockets of solid rock beginning to melt, and then eventually making their way up and out in a lot of cases as volcanic eruptions. So you get small pockets of magma from melting of tiny regions of the mostly solid, again, upper mantle and or crust area. So this is not to scale, by the way. So if you think of the crust and the mantle, which can, we can differentiate it. When we're talking again about where does this melt material come from, the upper mantle is pretty close to the crust. Oops, excuse me. Again, the melting is caused by heat brought from the core in that process of mantle convection, but again, it is mostly solid mantle or solid crust material that's turning to liquid that eventually makes its way up. And there's 3 different types of magma, and that's based on silica content. Silica, that's silicon and oxygen-based minerals, quartz being kind of the main one there. And from low to high, we have basaltic magma, andesitic magma, rhyolitic magma. So basaltic magma is low in silica content, low in quartz content, these types of rocks. Rhyolitic magma is higher in quartz mineral content. And that becomes important. So when we're talking about basaltic magma, this is material that's really melting from that upper reaches of the mantle. This is heavier material. It's kind of deeper down in this scenario. It's heavier material, and it's also typically darker because the elements that are heavier tend to be, in this case, darker. So the rocks that they eventually create are also darker. So when you're getting basaltic magma, that's melted material coming from the upper mantle. More on that in a little bit. Andesitic magma is kind of coming from this upper mantle crust boundary area, whereas rhyolitic magma is melted material directly from the crust. So that becomes important. So these 3 different magmas come from different spots. And the reason it's important as far as this class is pertained, because each of these magmas are different because of different chemical compositions. If this magma has different chemical compositions, that eventually gives us different types of volcanoes, different types of eruptions, different types of hazards associated with volcanoes. Right. So when we're talking about the magma, the differences between these, we can talk about a few different properties. Viscosity. Maybe you've heard this term. Maybe if you've ever, changed the oil in your car, you've come across this term, viscosity. Viscosity is defined as the resistance to flow. So if something has a low viscosity, it has a low resistance to flow, meaning it flows very easily. Like water has a low viscosity. If you're changing the oil in your car, you want an oil with a low viscosity because you want the engine parts to move nice and neat. And having a low viscosity oil will help everything kind of move smoothly. If something has a high viscosity, it's very sticky. It doesn't flow very well. Think cold honey, like how it doesn't really move too much. That would be something with a high viscosity. So as it pertains to magma, some magma is very flowy, some is very sticky. Right? So as the silica content increases in magma, so does the viscosity. So more silica, essentially more quartz content, the more viscous it is, the higher viscosity. It kind of flows like cold, sticky honey. This is important because it affects the flow of lava, the shape of the resulting volcano, as well as how explosive a volcano is. More on that in a minute. So when we're talking about magma, we can talk about viscosity. We can talk about also volatile content, how much trapped gas is in the magma. Gaseous H2O, water vapor, or CO2, carbon dioxide, as a gas. So the level of dissolved gas, these known as volatiles, determines how explosive the eruption will be. More dissolved gas, the more explosive it is. The more gas built up, the more it can blow. The volcanoes can essentially blow when they erupt. And again, volatile content increases with silica content. So with more silica, that means it's going to be more sticky lava, so it kind of doesn't flow as much. And it also means it's going to have a higher gas content and can trap more material. Both of those would make a volcano very explosive. So let's put it all together, shall we? So basalt, basaltic, andesitic, or rhyolitic magma. Those eventually make basalt, andesite, and rhyolite rocks. More on that in a little bit. But think of these as magma. So basalt is the lowest of silica content. It has low viscosity, so it flows very nicely. It has low volatile content. So as far as the volcano type, it would create something called a shield volcano. More on those in a little bit. And as far as ranking of increasing explosivity, since it's at the bottom, these types of volcanoes, shield volcanoes with basaltic magma, they're not very explosive. They're very flowy. Basaltic magma is a very flowy material. So when these erupt, the lava just usually flows out, spills out. Nothing too explosive. All right, so they're kind of the gentle giants. Then as we kind of go up on this chart, we have andesitic magma, a little bit more silica, a little bit more viscous, a little bit more what do you call these things? Volatile, so gas, a little bit more explosivity, and it creates a type of volcano typically called a stratovolcano, sometimes referred to as a composite volcano. And so these are, yeah, these things tend to explode when they erupt. They don't really have flowy lava, they tend to more explode, like Mount St. Helens in 1980. And then you have rhyolitic magma. A lot of silica, meaning it's a high viscosity, very sticky magma. It barely flows, and it traps a lot of gas, so it has a lot of volatile content, making it very explosive, forming types of volcanoes. I know it says continental caldera here, but forms super volcanoes. So this stuff is so sticky. This material, this rhyolitic magma, is so sticky as it's moving up. It's just so much behind it. It just doesn't want to go. And you get this gas in there, trapped in there as well, just making it super explosive. And you got more magma from below kind of pushing the stuff up, going, come on, get out of here. And when it does, so the more viscous it is, the more sticky it is, the more it kind of builds up. The more it can trap gas. All of that leading it to be more explosive, and all of that because of the silica content. And the silica content is just determined by where this material comes from. Basaltic magma coming from a little bit lower, the upper mantle, andesitic magma coming from that upper mantle crust area, rhyolitic magma coming from melted crust material. So kind of putting all of that together as this chart, I'm not going to go over this whole thing, it will help you kind of start to visualize what may be going on, and we'll take a good amount of time throughout the lecture to go through this stuff. You know what, before we go on, let me give you another part of the super secret code. It is the number 4. You got me? The number 4. One more time. The number 4. So, again, dependent on the plate tectonic setting, the types of boundaries, convergent, divergent, what you got going on, the type of crust, all of that leads to different volcanoes, and all of those volcanoes are driven by different magma types, and they each have their own type of eruption behavior. For instance, at a convergent boundary, where an ocean and continent are colliding, you can get coastal mountain ranges. It's typically andesitic, maybe rhyolitic magma, because you're kind of melting material from that upper mantle crust area. And these type of eruptions can be very, very explosive. Very, very explosive. Or, let me show you another. So what about divergent boundaries? A divergent boundary, that can happen in the ocean, but that can also happen on continental crust as well. When you do have this divergent boundary, typically the magma is basaltic, so coming from a little bit lower down, that upper mantle area. In these cases, you're going to have very gentle eruptions. Very gentle eruptions. It's basaltic magma. It's from deeper down. It's low in silica, meaning it has a low viscosity, and it's very runny. It's not going to build up too much. It's not going to be very explosive. You're going to get a lot of lava pouring out of there, but it's not a big explosive eruption. And then these things called hotspots. Most volcanoes happen around boundaries. Every once in a while you get it happening at these little hotspots, and you can see what kind of might occur. Well, you know what? Before we go, let me give you one more part of the super secret code. It is the number 7. You got me? The number 7. One more time. The number 7. We'll pause here. When we come back, we'll talk about where volcanoes are located. See you then.